Hello, and welcome back to Science Hub. If you have ever been told that a formula works for every number and quietly wondered how anyone could possibly know that, this one is for you. We will go slowly, and by the end, you will own it. Here we go. 1. 1 plus 3. 4. 1 plus 3 plus 5. 9. 1 plus 3 plus 5 plus 7. 16. Look at the answers. 1, 4, 9, 16. 1 times 1, 2 times 2, 3 times 3, 4 times 4. Perfect squares, every one of them. Add the odd numbers in order and a square falls out. Now ask the only question that matters. Does it keep going? Not for the first 4 lines, not for the first 4 million. For every line there will ever be. And here is the trouble. Each line is its own claim. There are infinitely many of them. You will never check them all. Mathematicians found a way to prove infinitely many claims with one argument, and it fits on half a page. By the end of this video, you will be able to write it yourself, and you will know exactly why it is allowed. Let us slow down and say exactly what is being claimed, because a proof can only be as precise as the claim it proves. The numbers we are feeding in are 1, 2, 3, 4, and so on without end. Your book calls them the natural numbers and writes them with a hollow capital N. For each natural number n, there is one line of our table. Line 1 says 1 equals 1 squared. Line 2 says 1 plus 3 equals 2 squared. Line n says the sum of the first n odd numbers equals n squared. So we need a way to write the first n odd numbers without dots trailing off the page. Watch. The first odd number is 1. The second is 3. The third is 5. Each is 2 more than the one before, and the list starts at 1. So to reach the nth odd number, you start at 1 and add 2, n minus 1 times. That is 1 plus 2 times the quantity n minus 1. Tidy it. 2 times n minus 1 is 2n minus 2. Add the 1. 2n minus 1. Check it against the table. n equals 1. 2 minus 1 is 1. Yes. n equals 2. 4 minus 1 is 3. Yes. n equals 3. 6 minus 1 is 5. Yes. So the nth odd number is 2n minus 1, and line n reads 1 plus 3 plus 5 all the way up to 2n minus 1 equals n squared. Your book of proof gives every line a name, S with a small n underneath. Say it. S sub n. S1 is line 1. S2 is line 2. Sn is the general line. Each Sn is a statement, a sentence that is either definitely true or definitely false, with nothing in between. And the claim we actually care about is this one sentence. Sn is true for every natural number n. One sentence, infinitely many statements folded inside it. Here is what we have now: a precise name for every line and a precise formula for the last term of every line. That is what a proof needs before it can start. Now, you might feel that the pattern is so strong that a proof is a formality. Let me show you why mathematicians refuse to feel that way. Here is a claim your book of proof offers you on page 36 and asks you to decide. For every whole number n bigger than 1, 2 to the power n minus 1 is a prime number. Test it. N equals 2. 2 squared is 4, minus 1 is 3. 3 is prime. N equals 3. 2 cubed is 8, minus 1 is 7. 7 is prime. 2 for 2. Feeling confident? N equals 4. 2 to the 4th is 16, minus 1 is 15, and 15 is 3 times 5. Not prime. The pattern broke on the third test. And a pattern can hold far, far longer than that and still not be a theorem. The same book tells the story of Goldbach's conjecture. Every even number bigger than 2 is the sum of 2 primes. 4 is 2 plus 2. 6 is 3 plus 3. 8 is 3 plus 5. 10 is 5 plus 5. 12 is 5 plus 7. 100 is 17 plus 83. Every even number you try works. Nobody has ever found one that fails. And yet, in more than 260 years, nobody has been able to prove it, so nobody may call it a theorem. Here are the words for this, and you should own them. A statement believed on evidence, but not yet proved, is a conjecture. The word is Latin. Con, together, iacere, to throw. A conjecture is a guess thrown together from the evidence. A statement that has been proved is a theorem, from the Greek theorein, to look at, a thing that has been seen through and understood. Right now, our claim about the odd numbers is a conjecture. Our job is to make it a theorem. And checking lines, however many, will never do that, because the lines never end. So we need something better than checking. Here is the idea, and it is so simple, you may not believe it is enough. Stand the statements up in a row, like dominoes. S1, S2, S3, and so on. One for every natural number, and the row never ends. A domino falling means that statement has been proved true. Now suppose you can do two things. 1. Knock the first domino down, that is, prove S1. 2. Show that whenever any domino falls, it knocks over the next one. Not domino 5 in particular, any domino. Whichever one you point at, if it falls, the next one falls. Now watch what happens. S1 falls because you knocked it down. S1 falling knocks S2. S2 falling knocks S3. S3 knocks S4. And nothing stops it. Every domino in that endless row goes down. Every statement gets proved. Your book states the whole thing in one box, and I want you to read it with me. Statements are lined up like dominoes. 1. Suppose the first statement falls, is proved true. 2. Suppose the kth falling always causes the k plus first to fall. Then all must fall. All are proved true. That is the entire idea of mathematical induction. 2 finite jobs and infinitely many statements proved. Now the words, because you will meet them in every book. Induction comes from the Latin inducere. In, into, and ducere, to lead. To lead into. Each case leads you into the next. The first job, proving S1, is called the basis step. Basis is Greek for a stepping, a foundation, the thing everything else stands on. The second job, proving that every fall knocks the next, is called the inductive step. Say them. Basis step, inductive step. Those two words are the whole method, and you now know what each one means in dominoes. Now, I promised you would know why this is allowed, so do not let me get away with a picture of dominoes. A picture is not a proof. Here is the hard question. Suppose you have done both jobs. The first domino is down, and every fall knocks the next. Why exactly is it impossible for some domino far out in the row to still be standing? Pay attention, because this is where the dominoes become mathematics. We will argue the way mathematicians argue when they want to show something is impossible. We suppose it happened, and we show that leads to nonsense. If supposing a thing forces nonsense, the thing cannot happen. Your book calls this proof by contradiction, and we will use it exactly once, right now. So suppose, for contradiction, that some domino is still standing. Maybe one, maybe many, we do not know which. Now here is the fact that does all the work, and it is a fact about the natural numbers themselves. Take any collection of natural numbers, as long as it is not empty. That collection has a smallest member. Think about why you believe that. Start counting from 1. Either 1 is and the collection, or it is not. If not, try 2. Then 3. You are walking up the number line, and the collection is not empty, so you must reach its first member. The only way to never reach 1 would be for every number to be missing, and then the collection would be empty, which it is not. Lebl, your real analysis book, calls this the well-ordering property of the natural numbers. Every non-empty set of natural numbers has a least element. And he is honest about its status. He takes it as an axiom, a starting truth, accepted without proof. Axiom, from the Greek axioma, that which is thought worthy. It is one of the ground rules of counting, and in your analysis book, every proof by induction rests on it. Now apply it. The standing dominoes form a collection of natural numbers, their positions, and we supposed that collection is not empty. So it has a smallest member. There is a first standing domino. Call its position M. Hold that picture in your mind and on the screen. Every domino before M has fallen, and domino M is the first one that did not. That is all we know about M. It is enough. Now we squeeze. Where can that first standing domino be? Could M be 1? No, we did the basis step. Domino 1 is down. So M is bigger than 1. And if M is bigger than 1, then M minus 1 is at least 1. So it is a natural number, and it sits right before M in the row. Now what do we know about domino M minus 1? It comes before the first standing domino, so it is not standing. It fell. And what did the inductive step promise? That whenever a domino falls, it knocks over the next one. Domino M minus 1 fell. The next one is domino M, so domino M fell. But domino M was standing. That is what M meant, the first standing domino. And we have just shown it fell. A domino cannot be standing and fallen at once. Nonsense. So the thing we supposed was false. There is no standing domino. Every statement is true. Read what just happened, slowly, because this is the why. The basis step guarantees the first failure cannot be at position 1. The inductive step guarantees the first failure cannot be anywhere else, because whatever sits just before it would have knocked it over. And the well-ordering of the natural numbers guarantees that if there were any failure at all, there would be a first one. Those three facts leave a failure nowhere to live. Lebl writes this as Theorem 0.3.6, the principle of induction, and proves it exactly this way in a few lines. You have now seen the proof of the method itself. Many courses never show it. We did. And from now on, when you write by induction, you will know what you are standing on. So here is the method as your book writes it, and this is the shape of every induction proof you will ever write. Proposition. The statements S1, S2, S3, and so on are all true. Proof. By induction. 1. Prove that the first statement, S1, is true. 2. Given any integer k at least 1, prove that sk implies sk plus 1. It follows by mathematical induction that every Sn is true. Now look hard at step 2 because it troubles almost everyone the first time. It says, prove that sk implies sk plus 1. That is an if-then statement. If sk, then sk plus 1. And the first way your book teaches for proving an if-then statement in Chapter 4 is called direct proof. Suppose the if part and show it forces the then part. So in step 2, you will write the words, suppose sk is true. And here is the question you should be asking right now. Are we not assuming the very thing we are trying to prove? No. And you must see exactly why not, or induction will feel like a trick for the rest of your life. We are not claiming sk is true. We are inspecting a promise. If domino k falls, then domino k plus 1 falls. Your book explains a promise like that with a truth table. And the table says one thing. A promise is broken in exactly one situation, when the if part happens and the then part does not. So to show the promise is kept, we only need to look at the situation where the if part happens. We say, suppose domino k has fallen. Now show that domino k plus 1 must fall. That is the whole of the inductive step. Whether domino k actually falls is not our business in that step. That is the chain reaction's business, and the chain reaction was settled by the argument about the first standing domino. The temporary supposition, sk is true, is called the inductive hypothesis. Hypothesis, from the Greek, hupo, under, thesis, a placing, something placed underneath for the moment, a floor to stand on while you build the next step. One more thing, and it matters. K is not a particular number. Step 2 says, given any integer k at least 1. You do not get to pick a convenient k. You write the argument once for an unknown k, and because k was arbitrary, that one argument is the push for every domino in the row. That is what lets two finite jobs cover infinitely many statements. Basis step. Knock down the first. Inductive step. For any k, suppose sk, derive sk plus 1. Then conclude. After the break, we do it, line by line, on the conjecture we started with. Before we write a single line of the proof, we need to know exactly what sk and sk plus 1 say, because the inductive step is going to start at one of them and arrive at the other, and you cannot arrive somewhere you have not written down. Sn says 1 plus 3 plus 5 up to 2n minus 1 equals n squared. Your book points out that sk is the same sentence with k in place of n. 1 plus 3 plus 5 up to 2k minus 1 equals k squared. And sk plus 1 is the same sentence with k plus 1 in place of n. Do that substitution carefully, because this is where people slip. The last odd number on the left becomes 2 times the quantity k plus 1 minus 1. Multiply out. 2 times k plus 1 is 2k plus 2, minus 1, 2k plus 1. So sk plus 1 says 1 plus 3 plus 5 up to 2k plus 1 equals the quantity k plus 1 squared. Now look at the two left sides side by side. The sum in sk stops at 2k minus 1. The sum in sk plus 1 goes one term further to 2k plus 1. So the left side of sk plus 1 is the left side of sk with one more term added on the end, 2k plus 1. That observation is the hinge of the whole proof. Make sure you see it on the screen before we go on. And the target, the right side of sk plus 1, is k plus 1 squared. Multiply that out too, so that we recognize it when we meet it. K plus 1 times k plus 1. K times k is k squared. K times 1 is k. 1 times k is k. 1 times 1 is 1. Add them. K squared plus 2k plus 1. So if our work ends at k squared plus 2k plus 1, we have arrived at sk plus 1. Now we know where we start and where we must land. That is always the first thing to write down in an inductive step. Step 1, the basis step, S1. Put n equal to 1. The left side is the sum of the first one odd number, which is just 1. The right side is 1 squared, which is 1 times 1, which is 1. 1 equals 1. True. The first domino is down. I want you to notice how small that was, and not to be suspicious of it. The basis step is usually easy, and your book says so. Its job is not to be hard. Its job is to exist. Without it, the chain reaction has nothing to start from, and at the end of this video, we will see exactly what goes wrong when it is missing. Step 2. The inductive step. Let k be any natural number, 1 or more, and we make no other assumption about it whatsoever. We must show, if sk is true, then sk plus 1 is true. So, as direct proof instructs, suppose sk is true. Suppose 1 plus 3 plus 5 up to 2k minus 1 equals k squared. That is our inductive hypothesis, and it is the only unproved thing we are allowed to use. Now start with the left side of sk plus 1. Because that is the thing we need to evaluate, and our plan is to turn it into the right side. 1 plus 3 plus 5 up to 2k plus 1. First move. Separate the last term. Write it as the sum up to 2k minus 1 in brackets plus 2k plus 1. Nothing has changed. We have only put brackets around the first k terms. Why do that? Look at what is inside the brackets. It is exactly the left side of sk, and the inductive hypothesis tells us what that equals, k squared. So replace the bracket by k squared. This is the one moment the hypothesis is used, and it is used the way every inductive hypothesis is ever used. You find the previous case hiding inside the current one, and you cash it in. Now we have k squared plus 2k plus 1. And we already multiplied out the target. K plus 1 squared is k squared plus 2k plus 1. They match. So the left side of sk plus 1 equals k plus 1 squared. sk plus 1 is true. Now let me show you why that last line is true, and not just that it checks, because I want this to be a thing you see. Look at the plane. Here is a square of dots, k dots by k dots. Its count is k squared. That is the inductive hypothesis sitting on the ground. Now add the next odd number, 2k plus 1 dots. Lay k of them along the right edge. Lay k of them along the top edge. And one in the corner where the two edges meet. K plus 1 is 2k plus 1. Exactly the next odd number. And look at what you have built. A square again. K plus 1 by k plus 1. That is why adding odd numbers gives squares. Each odd number is the L-shaped layer that grows a square by 1. The algebra, k squared plus 2k plus 1 equals k plus 1 squared, is that picture written in symbols. We have shown that sk implies sk plus 1 for an arbitrary k. The inductive step is done, and you have seen both what it says and why it is true. Now conclude and say the words, because the conclusion is a step and not a formality. The basis step showed that S1 is true. The inductive step showed that for every k, sk implies sk plus 1. It follows by mathematical induction that Sn is true for every natural number n. The sum of the first n odd numbers is n squared. Forever. Watch it run. Domino 1 is down. By the step, domino 2. By the step, domino 3. Domino 4. And on, past every number you will ever name, because the argument never needed to know which k it was pushing. The conjecture is now a theorem. Here is the finished proof, as your book of proof writes it on page 182. Read it once more from the top. Basis step. Inductive step. Suppose sk. Split off the last term. Use the hypothesis. Simplify. Arrive at sk plus 1. Conclude. A few lines. Infinitely many statements. Here is what you now own. To prove a statement about every natural number, you do not chase the numbers. You knock down the first, and you prove that each one knocks down the next. After the break, a real university question asks for 3 of these, and we will do all 3. Here is a question from a real analysis course at the University of Lagos, Mat 221. Prove each of these identities. 1. The sum from I equals 1 to n of I equals n squared plus n over 2. 2. The sum of I squared equals n terms n plus 1 times 2n plus 1 over 6. 3. The sum of I cubed equals n squared times n plus 1 squared over 4. Before anything else, that symbol. The big jagged letter is the Greek capital sigma, their letter S, and it stands for sum. Read it like this. Below it, I equals 1. Start the counter I at 1. Above it, n. Stop when the counter reaches n. To the right, the thing to add up, written in terms of I. So the sum from I equals 1 to n of I means take I equal to 1, then 2, then 3, up to n, and add them all. 1 plus 2 plus 3 up to n. Your book writes this notation down on page 25, And from now on, we can write a sum of any length without trailing dots. Let us feel the first identity before we prove it. n equals 1. The sum is just 1. The formula, 1 squared plus 1 is 2 over 2 is 1. Match. n equals 2. 1 plus 2 is 3. Formula, 4 plus 2 is 6 over 2, 3. Match. n equals 3. 1 plus 2 plus 3 is 6. Formula, 9 plus 3 is 12 over 2, 6. Match. n equals 4. 6 plus 4 is 10. Formula, 16 plus 4 is 20 over 2, 10. Match. Now, where does a formula like that even come from? I want you to see it because a formula that falls from the sky is a formula you will forget. Look at the plane. 1 dot, then a column of 2, then 3, then 4. A staircase. Its dots are 1 plus 2 plus 3 plus 4. Now take a second copy of the same staircase, turn it upside down, and fit it against the first. Watch the steps lock together. You get a rectangle, 4 dots tall and 5 dots wide. 4 plus 1. A rectangle 4 by 5 holds 4 times 5, 20 dots. 2 staircases made it, so one staircase is half of 20. 10. And in general, n tall and n plus 1 wide, n times n plus 1 dots, and half of that for one staircase. N times n plus 1 over 2. Multiply the top out. N times n is n squared, n times 1 is n. N squared plus n over 2. That is the formula in the question. So, do we still need induction? Here is the honest answer. That picture tells you why the formula is true, and it is worth more than the formula. But the question says prove, and we now own a method that proves a statement for every n with no picture and nothing left to trust. So we will use it. The picture tells you what to expect. The induction makes it a theorem. Identity 1. Let Sn be the statement. 1 plus 2 plus 3 up to n equals n squared plus n over 2. Basis step. N equals 1. Left side, 1. Right side, 1 squared plus 1 over 2, which is 2 over 2, which is 1. 1 equals 1. The first domino is down. Inductive step. Let k be any natural number. Suppose sk. 1 plus 2 up to k equals k squared plus k over 2. We must reach sk plus 1. So write sk plus 1 down first, so we know where we are going. Replace n by k plus 1. 1 plus 2 up to k plus k plus 1 equals k plus 1 squared plus k plus 1 all over 2. Let us simplify that target top so we recognize it when we meet it. K plus 1 squared is k squared plus 2k plus 1 plus k plus 1. Collect. K squared. 2k plus k is 3k. 1 plus 1 is 2. So the target is k squared plus 3k plus 2 over 2. Now work. Start at the left side of sk plus 1. 1 plus 2 up to k plus k plus 1. Bracket the first k terms. That bracket is the left side of sk, so by the inductive hypothesis, it equals k squared plus k over 2. So we have k squared plus k over 2 plus k plus 1. Now, we want a single fraction, and we have a fraction plus a whole expression. To add them, the whole expression must be written over 2 as well. K plus 1 is 2 times k plus 1 over 2. And 2 times k plus 1 is 2k plus 2. So we have k squared plus k plus 2k plus 2 all over 2. Collect the top. K squared. K plus 2k is 3k plus 2. K squared plus 3k plus 2 over 2. That is the target, exactly. So sk plus 1 holds. By induction, Sn is true for every natural number n. Identity 1 is proved. Look at the plane once more. The staircase of k columns holds k squared plus k over 2 dots. That is the hypothesis. Add one more column of k plus 1 dots, and the count is the formula for k plus 1. Same move as before. The previous case is hiding inside the current one, and you cash it in. Identity 2, the sum of the squares. Let Sn be 1 squared plus 2 squared up to n squared equals n times n plus 1 times 2n plus 1 over 6. Feel it first. N equals 1. Left side, 1 squared is 1. Right side, 1 times 2 times 3 is 6. Over 6 is 1. Match. N equals 2. 1 plus 4 is 5. Right side, 2 times 3 times 5 is 30. Over 6, 5. Match. Good. Now prove it. Basis step. N equals 1, and we have just done it. 1 equals 1. The first domino is down. Inductive step. Let k be any natural number. Suppose sk. 1 squared up to k squared equals k times k plus 1 times 2k plus 1 over 6. Write the target, sk plus 1, by replacing n with k plus 1. The left side gains the term k plus 1 squared. The right side becomes k plus 1 times k plus 1 plus 1 times 2 times k plus 1 plus 1 over 6. Simplify those brackets now. K plus 1 plus 1 is k plus 2. 2 times k plus 1 is 2k plus 2, plus 1 is 2k plus 3. So the target is k plus 1 times k plus 2 times 2k plus 3 over 6. Now work. Left side of sk plus 1. The sum up to k squared plus k plus 1 squared. Bracket the first k terms. By the hypothesis, that bracket is k times k plus 1 times 2k plus 1 over 6. So we have that fraction plus k plus 1 squared. One fraction, please. Write k plus 1 squared as 6 times k plus 1 squared over 6. The top is now k times k plus 1 times 2k plus 1 plus 6 times k plus 1 squared. Here is the move, and I want you to see the reason for it. The target is a product of 3 brackets, and one of them is k plus 1. Both pieces on our top contain k plus 1, so pull it out and keep it, because the target wants it. K plus 1 times the quantity k times 2k plus 1 plus 6 times k plus 1. Now tidy the inside. K times 2k plus 1 is 2k squared plus k. 6 times k plus 1 is 6k plus 6. Add 2k squared, k plus 6k is 7k plus 6. So the top is k plus 1 times 2k squared plus 7k plus 6. Compare with the target. K plus 1 times k plus 2 times 2k plus 3. We already have the k plus 1, so the question is whether 2k squared plus 7k plus 6 is k plus 2 times 2k plus 3. Do not guess. Multiply the target's two brackets out and see. K times 2k is 2k squared. K times 3 is 3k. 2 times 2k is 4k. 2 times 3 is 6. 3k plus 4k is 7k. 2k squared plus 7k plus 6. Yes, it is the same. So our top is k plus 1 times k plus 2 times 2k plus 3 over 6. That is the target. Sk plus 1 holds. By induction, identity 2 is true for every natural number n. And look at the world, a 1 by 1 square. Under it, a 2 by 2. Under that, a 3 by 3. The sum of the squares is a stepped pyramid, and the inductive step lays the next layer, k plus 1 by k plus 1 underneath. The formula counts the blocks in the pyramid, and we have just proved it never miscounts. Identity 3, the sum of the cubes. Let Sn be 1 cubed plus 2 cubed up to n cubed equals n squared times n plus 1 squared over 4. Feel it. N equals 1. 1 cubed is 1. Right side. 1 squared is 1. 2 squared is 4. 1 times 4 is 4 over 4. 1. Match. N equals 2. 1 plus 8 is 9. Right side. 4 times 9 is 36. Over 4, 9. Match. Basis step. N equals 1. Done. 1 equals 1. Inductive step. Let k be any natural number. Suppose sk. 1 cubed up to k cubed equals k squared times k plus 1 squared over 4. The target, sk plus 1. Replace n by k plus 1. The left side gains k plus 1 cubed. The right side becomes k plus 1 squared times k plus 2 squared over 4, because k plus 1 is k plus 2. Work. Left side. The sum up to k cubed plus k plus 1 cubed. Bracket the first k terms by the hypothesis that is k squared times k plus 1 squared over 4, plus k plus 1 cubed. One fraction. Write k plus 1 cubed as 4 times k plus 1 cubed over 4. The top is k squared times k plus 1 squared plus 4 times k plus 1 cubed. Now the same move as before, and now you know why. The target is a product containing k plus 1 squared, and both pieces on our top contain k plus 1 squared, because k plus 1 cubed is k plus 1 squared times k plus 1. Pull it out. K plus 1 squared times the quantity k squared plus 4 times k plus 1. Tidy the inside. 4 times k plus 1 is 4k plus 4. So, k squared plus 4k plus 4. And the target wants k plus 2 squared. Is k squared plus 4k plus 4 the same as k plus 2 squared? Multiply out and see. K plus 2 times k plus 2. K times k, k squared. K times 2, 2k. 2 times k, 2k. 2 times 2, 4. K squared plus 4k plus 4. Yes. So our top is k plus 1 squared times k plus 2 squared over 4. The target. S k plus 1 holds. By induction, identity 3 is true for every natural number n. All three identities are proved. Now look at what the third formula is actually saying, because there is something hiding in it. N squared times n plus 1 squared over 4. That is n times n plus 1 over 2, all squared. And n times n plus 1 over 2 is the first formula. 1 plus 2 up to n. So the sum of the first n cubes is the square of the sum of the first n numbers. Check it with your eyes. 1 cubed is 1, and 1 squared is 1. 1 plus 8 is 9, and 1 plus 2 is 3. 3 squared is 9. 1 plus 8 plus 27 is 36, and 1 plus 2 plus 3 is 6. 6 squared is 36. 1 plus 8 plus 27 plus 64 is 100, and 1 plus 2 plus 3 plus 4 is 10. 10 squared is 100. That is not a coincidence, and it is not magic. It is the two formulas you just proved, read together. Your book lists it as an exercise of its own, and you have already done the work. The same university question has a fourth part, and I want you to see it because it tells you why a course on integration is asking you to prove these three formulas at all. Part 4 says, evaluate the limit as n grows without bound of the sum from I equals 1 to n of 16 over n times the quantity 4i over n cubed plus 8 times 4i over n. Look at the shape of it. A sum of n pieces and the factor 16 over n in front of each piece shrinks as n grows, while the pieces multiply. Thinner and thinner columns, more and more of them. Mathematicians call a sum shaped like this a Riemann sum. Rectangles approximating an area, and the next video builds the integral out of exactly that and evaluates this very limit. And when you open that sum up, the n that matters is inside I cubed and I, added from 1 to n. Those are identity 3 and identity 1. The formulas you just proved are the engine that evaluates that limit. Hold on to them. Before you go, 2 ways this can go wrong, because knowing the failure is part of knowing the method. First, a true basis, and even many true cases, do not give you the inductive step. Go back to 2 to the n minus 1. At n equals 2, it is prime. At n equals 3, it is prime. 2 dominoes down. Does the next one fall? N equals 4. 15 is not prime. Domino 4 stands. So the promise, if S3, then S4, is broken. The if part is true, and the then part is false. No inductive step can be proved here, because at k equals 3, the push fails. No number of true cases ever manufactures the inductive step. You must prove the push for an arbitrary k, and if you cannot, you have nothing. Second, the other way round, an inductive step without a basis. Here is a statement built for this lesson. Sn says n equals n plus 1. Suppose Sk, k equals k plus 1. Add 1 to both sides. K plus 1 equals K plus 2, and that is Sk plus 1. So the inductive step is provable. Every domino would knock down the next. But look at the basis. S1 says 1 equals 2. False. The first domino never falls, so nothing falls. And indeed, every one of those statements is false. Both legs, always. The basis step without the inductive step proves one case. The inductive step without the basis step proves nothing at all. And a small warning from your book about where the row starts. If your statements begin at 0 or at 8, the basis step is S0 or S8, and the conclusion covers every n from there upward, nothing below. Induction starting at S1 says nothing about 0 or the negative integers. One last piece of vocabulary, and it is a trap. In science, induction means observe many cases and conclude the rule is likely. That is inductive reasoning, and it can be wrong, as 2 to the n-1 just showed you. Mathematical induction is not that. It proves with certainty. Same word, different thing. Your book warns you about exactly this confusion, and now you will not make it. 2 notations, so that no book ever looks foreign to you. Your book of proof names the statements Sn and proves Sk implies Sk plus 1. Lebl, your analysis book, writes the statement as P of n and says, basis statement, P of 1 is true. Induction step. If P of n is true, then P of n plus 1 is true, then P of n is true for all n. Same method, same 2 jobs, different letters. Some books prove Sn-1 implies Sn instead. Same thing again. Read past the letters to the 2 jobs. Here is what you can now do. Hand me any claim about every natural number. You know it is infinitely many claims. You know a pattern is not a proof. You knock down the first domino, the basis step. You take an arbitrary k, suppose Sk, and derive Sk plus 1, the inductive step. And you know why that settles every case. Because a failure would have a first instance, and a first instance has nowhere to live. You did it for the odd numbers, and for the 3 sums a university question asks for. There is a stronger version of the inductive step, where you are allowed to stand on every earlier domino at once, not just the last one. Your books call it strong induction, and it gets its own episode. Next time, the limit of a sum of thinner and thinner columns, the Riemann integral, built from nothing, with these 3 formulas doing the heavy lifting. Every step shown. If one felt skipped, tell me, because that is a bug.